Let's start this section with a question. And that question is, if you consider this vehicle traveling along this road, which is curving to the right, and the vehicle is initially at point A and later at point B, the question is the vehicle accelerating despite traveling at a steady speed of, let's say, 120 kilometers an hour? So in other words, the speedometer of the vehicle reads 120 kilometers an hour when it's here, and it still reads 120 kilometers an hour when it reaches this point over here. So 33.3 meters per second is how fast it is traveling at this instant, and it is still traveling at 33.3 meters per second by the time it reaches B. So the speed is unchanged. The question is it accelerating? So ponder on that for a few moments. Let's start by considering the velocity vector when the vehicle was at A. And remember that velocity, being a vector, has both magnitude and direction. So the magnitude is 33.3 meters per second, and the direction of the velocity initially is this way, which would be tangential to its path. So the instantaneous linear velocity is having a magnitude of 33.3 meters per second, and it's directed in that direction. Later, when it reaches B, the vehicle has an identical magnitude, but as you can well imagine, the direction of the velocity vector is slightly rotated to the right. So it is now this big. If you place both of those vectors tail to tail, a line joining their 2 points would represent a change in velocity. So far we've concluded that the vehicle from A to B has experienced a change in velocity. Not a change in magnitude of the velocity vectors, but a total change in velocity. Change in velocity, delta V, would be represented by the length of this red vector. Now, let's think back to what acceleration is. Acceleration is change in velocity per unit time. So if we actually have change in velocity, delta V, and it took a certain period of time to happen, we now in fact do have acceleration. That acceleration is referred to as centripetal acceleration, and it is always directed towards the center of rotation. Remember, the center of rotation of the vehicle would be a point out here somewhere. So at all times, that acceleration is directed inwards towards that point. The magnitude of the acceleration is the velocity squared over r, or alternatively omega squared r, if we were to consider an arm rotating at omega. If you could have an imaginary arm that is always connected to the vehicle, going back to the center point, that arm would effectively be rotating clockwise. If you had the speed of rotation of that arm in radians per second, you could use omega squared r to find this value of centripetal acceleration. The units, by the way, are meters per second squared, just like we are accustomed to with linear acceleration. The proof for what we've just done is on page 157 in your books. You're welcome to have a look at that. And while we're on the subject, another term for centripetal would be center seeking. So that's a good way to remember the direction of the acceleration. It is center seeking. It seeks the center of rotation. So in summary, any object that is moving in a circular path, be it at steady speed or changing speed, that object experiences centripetal acceleration. Now that object could even be a human. Have a look at this YouTube clip down here, and you'll see a video about a centrifuge, which is a device used to simulate acceleration on the human body. Basically, the human is strapped to a seat in a capsule that is rotating in a circular path, much like our motor car here, and is experiencing centripetal acceleration. Have a look at that, and that relates to our first problem that we're going to do as well. So if you go to page 165 of your textbooks, and let's look at number 5. To investigate the effect of acceleration on the human body, an astronaut is strapped in a sitting position in a seat attached to the end of an arm 3.5 meters long and which rotates in a horizontal circle. At what speed in revs per minute must the arm rotate to subject the astronaut to an acceleration of 6g? Now remember, 6g would be 6 times your normal gravitational acceleration. So that would be 6 times 9.81 meters per second squared, which would be 58.86 meters per second squared. So there's our rotation, there's the arm 3.5 meters long, there's the human strapped to the seat, and he's rotating in a circular path. We're looking in the plane of rotation. Remember that acceleration is equal to omega squared r, and our acceleration is 58.86, that's what is desired, and the arm is 3.5 meters long. What must be the speed of rotation omega? Turns out to be 4.1 radians per second. They wanted the answer expressed in revs per minute, and remember that omega is 2 pi n over 60, so n is 60 omega over 2 pi. So this device must turn at 39.16 revolutions per minute for this person to experience 58.86 or 6g of acceleration. And that acceleration would be directed towards the center being this axis here. So at all times, the person would experience an inward acceleration of 58.86 meters per second squared. Let's look at another example of where an object moves in a circular path. If we look at ancient bridges, and here is a photograph of what is known to be the oldest bridge in the world, which is essentially packed rocks, but they have to be in this arch so that they actually stay together. But the problem is, whatever vehicle passes over this bridge is going to have to travel in a circular path. Just for this short period of time, it will be traveling in a circular path. And we've learned that when something travels in a circular path, it has center-seeking acceleration. Okay, so whilst a vehicle is traveling over this bridge, it would experience centripetal acceleration towards the center of rotation, which would be an imaginary point down here somewhere. So let's look at number 6, which asks, determine the greatest speed in kilometers per hour with which a vehicle may pass without leaving the ground over a humpback bridge, the highest part of which is an arc of a vertical circle of 7-meter radius. So here's our vehicle, and it's traveling over this bridge such that it is traveling in a circular path with radius 7 meters. Let's start by drawing a free body diagram of the motor car in this position up here, and here is the free body diagram. Now remember how a free body diagram works. We draw the object in question in isolation with no surroundings, and then we insert all the forces keeping that object in that position. So the vehicle would have a combined force R between its rear wheels, the two rear wheels together, and the surface we'll call R, and the two front wheels and the surface we'll call F. Now if the vehicle is traveling so fast that it is just on the point of lifting off, we'll make both of these values 0. Then passing through the center of gravity is the vehicle's own weight, which we know to be mass times g. That would always act towards the center of the Earth. But now remember that the vehicle is traveling in a circular path, therefore has center-seeking acceleration with magnitude v squared over r. To make our free body diagram balance, what we do is we insert the force ma, the product of mass times acceleration, and the rule is simple. You always place that arrow in the opposite direction to the acceleration. Remember that a body that is accelerating does not have equilibrium between its forces like we had with static objects. But for convenience, what we do is, in dynamics, when we have acceleration, there's a relatively easy way of handling these problems so that they come into so-called balance. So we can sum forces up and sum or equal to forces down, left and right, etc. And the way we achieve that is always to insert this force, ma, in the opposite direction to acceleration. This book refers to it as the fictitious inertia force. More about that later. But for this, the purposes of what we're doing now, simply place MA in the opposite direction to acceleration. So in this case, acceleration is downwards or towards the center of rotation. So in exactly the opposite way, we'll put in MA, and now we can so-called balance these forces. We can say that ups equal downs, and in our case, we would simply have this one as an up equal to this one as a down, and we can proceed like that. So mv squared over r, remember m carries through, and a is in fact v squared over r, so mv squared over r is your ma term, and it is equal to mg, one force up, one force down. And you can solve for v, and you find that at 8.29 meters per second, or 29.83 kilometers an hour, this vehicle will be on the point of lifting off the ground and cannot go any faster. Next, let's consider Earth satellites. Right now there are hundreds of satellites busy orbiting the Earth as we speak, and at night, if you look up, you'll actually see them. In fact, what you're seeing is the reflection of the sun off their solar panels and other parts of their bodies, and you will see them rotating around the Earth, and they are there in stable equilibrium. But remember that they are also moving in a circular path, and therefore must also be experiencing centripetal acceleration. So let's, via a problem, look at what keeps them there and how fast they have to orbit to remain in this stable equilibrium. Number 7 refers to a satellite. It says it is required to put a satellite into a circular orbit 1,500 kilometers above the Earth's surface. Determine the velocity the satellite must have in order to do this. Assume that the radius of the Earth is 6378 kilometers. That's the radius, and the acceleration due to gravity at the altitude of 1,500 kilometers is 6.43 meters per second. Remember, it's 9.81 here where we are on the surface of the Earth, and as you move away from the Earth, it's less and less, and they're saying that at 1,500 kilometers altitude it's 6.43. Remember, in deep space it is 0. So here's a diagram of our satellite. That's this orange dot over here. Here's the Earth. There's the radius of the Earth. There's the extra 1,500 kilometers altitude that the satellite has. And then the blue dotted path or circle is the path of our satellite. And because that is a circular path, there is indeed centripetal acceleration, center seeking towards the center of the Earth. So therefore, the weight of the satellite is mg, but now g is no longer 9.81 like it would have been on Earth's surface. It is in fact 6.43. So m times g for this satellite is m times 6.43. Now remember, to make the so-called equilibrium, to make a little equation where ups equal downs, etc., it is convenient for us to insert ma. Remember the rule? Opposite to acceleration. So if acceleration is this way, we simply place ma the other way. I normally make it red to remind us that this is the fictitious inertia force. But once inserted, we can then simply sum like for a statics problem. So in our case, ma, which would be mv squared over r, by the way, because remember a is v squared over r, that would be equal to m times 6.43. And that will allow us to find the required velocity, because mv squared over r, here's the radius, if you add that and that, is equal to m times 6.43. So our satellite must be traveling at an enormous 7,117 meters per second to remain in stable equilibrium. It sounds like a lot, but remember that there's no air at that altitude, and once speeded up to that speed, it will keep that speed according to Newton's laws, unless acted upon by an external unbalanced force like aerodynamic drag, which is absent in this case. This object will simply keep on going at that velocity all day, every day, and remain in stable equilibrium. But let's just ponder on the thought of what happens to a satellite if for some reason that velocity reduces. Well, you would lose your stable equilibrium and the object, the satellite, would begin to descend, which would be a bad thing for a satellite because eventually it would get so low that it would enter the Earth's atmosphere, start to heat up, and ultimately destroy itself. Conversely, if something speeded the satellite up, it would start to move away from the Earth and could eventually get lost. Now, much like these satellites, we have the International Space Station orbiting at around 400 kilometers altitude. Have a look at this little YouTube clip over here to see what life is like inside the International Space Station, which is also orbiting the Earth. Now, while studying dynamics, which is what we're doing at the moment, always keep Newton's laws of motion readily available. This next problem we're going to do relates to this one over here, Newton's first law of motion. So have a look at that one and keep page 172 open at all times so that you can refer to these Newton's laws. Our next problem relates to this ancient weapon called a sling or a slingshot, which consists basically of a leather pouch in which your projectile is placed and a closed loop on the one end which is attached to your finger and a loose end. So there's the projectile in the leather pouch. This end with the closed loop is placed around your finger and you hold the loose end in your hand. You then rotate the projectile either in a vertical plane or a horizontal plane, it doesn't matter, and then at the correct instant you let go of the loose end and the object then continues as it was according to Newton's laws. If you release it at this point here and it was rotating around and around anti-clockwise when viewed from above, and you let go here, it would continue with that velocity in the direction it was going, and then the projectile could strike something in its path. So that is the principle of a sling or a slingshot weapon. So page 212, number 1, refers to a slingshot, 350 millimeters long, and it's whirled around so that the hand holding the loose end revolves in a circle of 500 millimeter diameter and exerts a restraining force of 36 newtons when a 57 gram stone is released, and you must calculate the velocity of the stone as it leaves the sling. So here we are viewing the slingshot from above. Here is the 500 diameter or 0.25 meter radius path of the hand, the operator. The hand is moving in that circular path. There is the 350 millimeters length of the slingshot, and here is the circular path followed by the projectile. So whilst it's rotating, there is a 36 Newton tension force in the actual sling, that is the two strings together, combined 36 newtons. Because it's moving in a circular path, remember there's always acceleration towards the center seeking. So for our so-called balance of our forces, we're going to insert the fictitious inertia force in the opposite direction to acceleration. Remember, it's always the product of M and A. M is 57 grams, and A is the V squared over R, the centripetal acceleration, which is instantaneous linear velocity squared over radius. So those two are going to be equal and opposite. MA is outwards, and this arrow of the two arrow pair is the 36 Newton one that is acting on the object. One to the right or outwards and one to the left or inwards. So the 36 is equal to all of that, and we can solve for the required instantaneous linear velocity required for this slingshot to operate as described. Let's look at number 6 on page 213. They say it is a two-seater fairground ride. So when viewed from the side, we've got a shaft that is rotating, let's make it anti-clockwise, and we have a person sitting in this seat of 91 kilograms mass and a person sitting in this seat of 83.6 kilograms mass. Now clearly there's imbalance here, so let's see how much imbalance there is, and they've asked for what its effect is going to be on this central shaft that is supporting all of this. So we'll have to assume that the machine itself was balanced before the passengers got onto it. So we'll just consider the effect of the two passengers and the imbalance that they cause by having different masses. So both experience inward acceleration, center-seeking acceleration, this one this way and this one this way. So as with the other problems, opposite to the acceleration, in other words outwards, we're going to insert m omega squared r, m omega squared r. So let's see how those two compare to each other, and we'll subtract one from the other and get the net force, which turns out to be 25 newtons of resultant outward radial force, which incidentally would be in the direction of the 91 kilogram person, because that is the bigger of the two forces. So at all times there would be a radially outward force of 25 newtons, depending on which position this person was at any one instant. It would always be radially outward from the axis of rotation through that person, radially outwards 25 newtons. In number 10, we have a 900 gram object tied to one end of a 915 millimeter length of wire, and it's whirled around in a horizontal circle. So picture you holding it above your head and you're swinging it around in a circle that is in a flat horizontal plane. Now the braking strength of the wire is 178 newtons. Calculate the greatest speed in meters per second and revs per minute that the object can have without breaking the wire. So with the wire on the point of breaking, in other words at 178 newtons, that would be the tension in the wire, and we would have an inward center-seeking acceleration as before, and we would insert the fictitious inertia force MA outwards, made it red so we remember what it is, and we have the mass times the omega squared r, which is the A value, and that is equal to the 178 when we're at the point of braking. So let's solve for the rotational speed. It turns out to be 14.7 radians per second. And of course you can convert that to revs per minute. Remember that omega is 2 pi n over 60, or n is 60 omega over 2 pi. So once you work that out, that would be the fastest speed in revs per minute that you can rotate this affair without snapping the wire or being on the point of snapping the wire. Now in number 10, we consider if the same object was swung in a vertical circle, determine the maximum speed in meters per second for both the highest and lowest points. Now what's interesting here is we have to consider gravity, or bring gravity into the situation now, because before the object was swung in a horizontal flat circle, and now we are swinging it in a vertical plane. So gravity is going to have an effect, and it'll be a different effect for when it's at the top and when it's at the bottom of that circle. So when viewed from the side, here is the circle of rotation that I spoke of, and here is the object at the highest point, and here's the very same object at the lowest point. In both cases, the wire is at breaking point. In other words, there's 178 newtons of tension in the wire. And in both cases, top and bottom, we have mg, that is its mass times the gravitational acceleration, 9.81 on Earth, which is always downwards, regardless of rotation. So there it is there, and there it is again. And because of the inward acceleration, which is this way when the object's at the top and which is this way when the object's at the bottom, both of those are m omega squared r. So let's start by looking at the forces when the object is at the top here. We would have m omega squared r upwards, and we would have those two both downwards. And you find that the wire would break with an omega of 15.06 radians per second. And at the bottom, you have two downs and one up. So 178 is the up, and the two downs are 0.9 times 9.81, as well as m omega squared r. And you will find that 14.33 radians per second will already break the wire. So the wire would break more easily when the object is at the bottom than when the object is at the top, which makes sense because gravity is adding to the tension in the wire effectively. Now, if you watched that little video about the life in the space station, you would have noticed that the occupants of the space station are experiencing weightlessness, which might be entertaining for a few minutes, but to live up there for weeks on end, it is quite challenging, apparently. So here in number 14 is a suggestion for combating weightlessness. So what the author has come up with is, obviously it's still fiction, this thing doesn't exist yet, but we have a capsule that is rotating, in our case clockwise, when we view it from the one end. And this here is a proposed seat for the operator to sit on, so the astronaut would be sitting on the seat over here, and it would be rotating clockwise around and around whilst in space. So without the rotation, the astronaut would feel weightless inside here because obviously he is in equilibrium in orbit and therefore has no net effect of weight acting on him. He feels weightless. But if he was rotating as well, whilst orbiting, he was rotating clockwise, he would be moving in a circular path. There would be the center of rotation, and he, the astronaut sitting over here, would be moving in a circular path around and around. And we've learned so far that we could then insert some forces, and if we could actually get to a situation where there was actually force between the astronaut and the seat on which he sat, he might feel as though he was back on Earth, which apparently is a good idea. So let's have a look at the forces involved to achieve all of this. Oh, and we were told that the radius is 605 millimeters. Let's read that again. The effect of gravity for an operator whose center of gravity in the sitting position is 605 millimeters from, that should read from his feet. So from his feet to his center of gravity, 605 millimeters, remember that. So 605 millimeters subtracted from the 2.5 meter radius, remember half of 5 meters would be 2.5 from here to here, minus the 605 means that the operator is having a radius of rotation of 1.895 meters. So from the center of rotation to the center of gravity of the person is 1.895 meters, rotating in a circular path around and around. Remember, when anything moves in a circular path, there is center seeking or centripetal acceleration. And opposite to that, we're going to insert MA, which is M times A or M times omega squared R. And we are hoping to get a force F, which is identical in magnitude to that which the person would have had on Earth. On Earth, that force would have been m times 9.81. So we are going to make it m times 9.81, or the equivalent thereof. So F is in fact m times 9.81. There is no 9.81 up where this person is, but we are trying to achieve that magnitude of force between him and the seat. Okay, the other forces are m omega squared r. There are only two, equal and opposite. F that way, and MA the opposite direction. So if we solve for omega, if you rotate this capsule at 2.275 radians per second, you will achieve that force which will feel to him like the force he had when he was sitting on a chair on planet Earth. So at 21.72 revs per minute, you would achieve this situation, which would give the operator the false impression of being back on Earth and having the effect of gravity pushing him into the seat. Let's finish off the section by looking at number 13, where we have a bucket with a mass of 910 grams, empty, contains 3 liters of water and is swung around in a vertical circle at 40 revs per minute. If the center of gravity of the bucket plus water is 1.05 meters from the person's shoulder, determine the force on each of the 2 pins securing the handle of the bucket when the bucket is A at the top of the circle and B at the bottom of the circle. Right, so here's our operator swinging the bucket in a vertical circle, and here the bucket is at the top of the circle and here the bucket is at the bottom of the circle. This, by the way, is the bucket. There's the water in the bucket. Here is the handle and here is the person's hand. The combined mass of the bucket and the water would be 3.91 kilograms. And remember that gravity always acts towards the center of the earth regardless of what motion the object has. So there's the center of gravity of the bucket and the water. Here is mg directed towards the center of the earth. In both cases, that is non-negotiable. It is present in both cases and is directed towards the center of the earth. Also in both cases, there's tension in the operator's arm, which we draw always as the two arrowheads facing each other. And then finally, opposite to the centripetal acceleration, we insert MA and MA. Now, centripetal acceleration in the first instance is downwards, so we put MA opposite. And in the second instance, centripetal acceleration is upwards, so we put MA as usual in the opposite direction. So in instance A, we have 2 downs equal to 1 up, and in instance B, we have 2 downs equal to 1 up. So in A, you've got T1, the tension in the operator's arm, plus mg equal to MA. So it turns out that T1, the force in the operator's arm, is 33.68 newtons, and the bucket has 2 handles, so you divide that by 2, or 2 pins attaching the handle to the bucket, so each would have 16.84 newtons force in it. In instance B, you've got 3.91 omega squared r, which is MA plus mg, and that's equal to T2, so T2 is 110. Divided by 2 once again, 55.2 newtons in each pin. As usual, stand back, see if it makes sense. Which one has the higher force? Well, it looks like B at 55, and that makes sense because when the bucket is at the bottom, it would stand to reason that the force in the handle would be greater than when it was at the top.